Look at this blank space on the exam paper. You know the physics, you've memorized the formulas, yet right here, you are bleeding marks. Welcome to the ultimate boss fight, the Cambridge IGCSE Physics practical questions. Okay, let's dive straight into this explainer and reveal the exact attack pattern to beat it.
So, here is the painful reality. You totally know the physics, yet you're somehow losing up to 30% of your marks on these practical questions. Why does this happen? Because ordinary revision completely fails if you aren't using the exact phrasing the examiner is hunting for. You write down what you think is right, perhaps explaining the concept perfectly in your head, but the examiner just sees a blank space because the key terms are missing. Well, we are going to fix that right now.
Here is our strategic attack pattern to unlock those top mark bands and secure your grade. We'll break down the boss fight itself, master your variables, decode the data types, spot those deadly mistakes, deploy a top band framework, and finally, run a foolproof exam checkpoint.
Section 1. The Physics Boss Fight, Surviving the Mark Scheme. Let's see how getting inside the examiner's mindset completely shifts your entire exam strategy.
The secret to surviving this is actually pretty simple. You must feed the examiner the exact mark magnet vocabulary they require. Listen, they aren't looking for a vague, rambling story about what you did in the lab. They are speed scanning your paper for correct terminology, specific units, and direct source page evidence. Think about it. If you write, "I will make it fair," you literally get 0. But if you write, "I will control the initial temperature," the mark magnet activates and boom, you score.
Moving to Section 2, Mastering Experimental Variables, Equipping Your Core Weapons. The crucial point here is setting up your core loadout, starting with the 3 fundamental variables, because honestly, if you get these wrong, your entire practical design just collapses.
First up, we have the independent variable. This is the variable in an investigation that is purposefully changed by you, the experimenter. Think of a classic Hooke's law experiment. The force, or the load that you actively add to stretch a spring, is your independent variable. You decide what it is, and you dictate the intervals at which you increase it.
Next is the dependent variable. This is what you actually measure or observe as a direct result of changing that independent variable. Continuing with our Hooke's law example, the physical extension of that stretched spring is totally dependent on the load. It's the raw data you're actively collecting, measuring with your ruler, and recording directly into your results table.
Finally, we have the control variables. These are any factors you absolutely must keep exactly the same throughout the entire investigation to ensure a fair test. If you're calculating a spring constant, your control variable is the specific spring you use. You obviously don't swap it out for a stiffer one halfway through the experiment. Depending on the setup, things like environmental temperature could also be a vital control variable.
Check out this setup right here. It beautifully illustrates our variables in action. In this worked example for finding the critical angle of semicircular blocks, the independent variable is the block's material. That's what you choose to swap out first. The dependent variable is the size of the critical angle you then measure with your protractor. Identifying these up front instantly structures your data collection and makes your method crystal clear to the person marking your paper.
Section 3. Decoding physics data types, structuring your evidence. Now that we have our variables locked and loaded, we need to know exactly how to categorize the data we collect from them. This is how you design flawless tables and graphs. Now, mixing these data types up is exactly where so many students needlessly lose marks. Categorical data is grouped, like the names of materials, glass, perspex, or water. Continuous data can take any numerical value within a range, like a temperature reading or a spring's extension, allowing for all sorts of decimals. Discrete data, though, can only take specific, usually whole values, like a number of protons or the number of discrete weights you add. And here's the kicker. If you plot discrete data on a continuous line graph incorrectly, the examiner will penalize you instantly.
Okay, I'm going to pause right here. In just a moment, I'll show you the exact examiner clue that changes your practical answer completely. Literally, the difference between an average grade and a top band score. But first, you absolutely need the framework that makes that clue completely obvious. Without it, you're going to walk straight into a massive trap.
Which brings us to Section 4, Spotting Common Student Mistakes, Avoiding the Examiner's Traps. Let's see how this builds into the exact mistakes examiners see over and over and over again. These are the hidden traps just waiting for you. Missing units on calculations? That's an instant, totally unnecessary penalty. Rounding numbers way too early in your working out? That totally ruins your final answer because of compounding errors. Then you have vague explanations lacking proper physics terminology, or graph axis errors, where you accidentally flip the independent and dependent variables on the x and y axis.
Throw in weak practical improvements and making bold conclusions your data simply does not support, and your marks are gone.
Look at this contrast. This is a perfect spot the error moment. The flawed answer on the left says, I will change the weight and see how long the spring gets. You can see why this loses marks, right? It's incredibly vague. But the improved mark magnet answer on the right instantly scores. I will change the independent variable, the load, and measure the dependent variable, the spring extension, to determine the spring constant. Precise terminology. That is exactly what the examiner wants to read.
Section 5, Top Band Answer Framework, the 4-step formula for maximum marks. Let's dive right into the ultimate framework that turns a pretty good answer into a top band answer every single time.
Every high-scoring answer follows this exact path. Step 1. State the physics concept clearly, like moments, center of gravity, or thermal capacity. Step 2. Cite your specific evidence or data directly from the experiment's table or graph. Step 3. Apply scientific reasoning to logically connect that data right back to the concept. And Step 4. Wrap it all up in that exact examiner-approved terminology we've been discussing. Lock this in. This is your 4-step formula for maximum marks.
Section 6, Final Exam Checkpoint, Securing Your Grade. The absolutely crucial point before you finish any practical exam question is to run through a strict final checkpoint. Do not skip this step.
Never, ever move on without running this mental checklist. Verify your units are actually present and correct. Check that your significant figures match the precision of your raw measuring instruments. Ask yourself if your graph scale uses at least half the page. And honestly, just ask if your data points are reasonable in the real world. Think about it. If you calculate a spring extension of 4 kilometers, you've clearly missed a unit conversion.
So you've conquered variables, data types, and the core answering framework. But here is the massive problem. What happens when the exam throws a high-level command word at you, asking you to evaluate the overall reliability and accuracy of the entire experiment? If you don't know exactly what that specific command word demands, this whole framework falls apart. That is the true final boss. To decode those specific command words that actually decide your mark band, you have to take the mandatory next step. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Click the explainer on your screen right now to master those command words, and I will see you over there.